We are recording. Okay, we'll start.
Yeah.
Okay, so welcome to lecture 6 of this course, ISSS Introduction to your generative modeling using VAs. So quick recap of what we did last class. So previously we understood the different terms in the evidence lower bound, the elbow of the elbow in optimizing this VAs, and we came to a critical issue where we wanted to find out the gradients with respect to this particular term, which is the reconstruction term as under the autoencoder parlance. We saw that why this could be an issue in the first place if we were to directly use usual gradient descent method, and especially when we use sampling to approximate the term that we have in hand. And then we saw, there's something called using this linear transformation theorem. We proved that we found a method to separate out the random part of the stuff and something which can be which is deterministic and depends only on the parameters phi, and therefore we could define the gradients of the particular sample that we get. And then we discuss some other methods which have been given by the authors in the paper also, especially for location scale family sort of methods. And we also spoke about something called a structural inverse CDF method, where because the CDF of a particular random variable is always uniform over 0 or 1, so we could always use the inverse of the CDF to get the random variable back. And we also discussed ideas on if that was the case, what should the encoder predict and how you will end up using such a thing. And then composition sort of variables. We then came to the big question that we had, that if you want to maximize the expected log likelihood of the model, so therefore we need to look at all data points, and then we extended this idea to looking at the expectation over all data points of the elbow for each point. And then we just looked at how we can probably operationalize this whole idea. And then we came back to the central question which started all this discussion. That is basically, how do we end up sampling from this particular VAE, and the idea of inference, that is how do we get what latent is being generated for a given data point, the posterior that we define. So then we spoke something about a thing called beta VAE. So we'll discuss this in a bit more detail, and discuss some other issues which people have found with VAs and probable solutions that they have proposed. So again, so coming back to the elbow, is basically we can write it in this form: elbow over all data, that is expectation over px of the elbow. And then one can make a claim that this is something true. That is basically maximizing log of p theta of x is equivalent to maximizing the log of this quantity, quantity over p theta of z, right? So yeah, so how do we go about proving it mathematically? Um, any thoughts? How do I start this?
So we prove that if x is greater than y, the expectation of x is always greater than the expectation of y.
Right.
So I think the same principle can be used to
Okay.
prove this, because maximization of log of p theta of x will be also and anyhow log p theta of x and p theta of x are logs are monotonically increasing function.
Increasing function, right? So on those lines we can use. So basically this can be broken down as log of p theta of x comma z integral over z, right? So we're taking it as a marginal over the joint latent and data space, and this can then be broken down as log p theta of x given z into p theta of z. So again, very simple idea. And then this can be seen as log of expectation over P theta of Z of this quantity, right? This is exactly same thing we use in VAE derivation also. But here the idea is, instead of doing the Jensen inequality and all, one can obviously say that, okay, maximizing these, sorry, let me just remove this. This is exactly equal. So maximizing this, all of these quantities over theta, this is equivalent to maximizing this, right? Because log is a monotonic function. That's the idea. So so now the thought process here is that the authors, they say that so let's say any data that you have X can be seen as generated from two sorts of two inherent sources of variations that are there. Let's say we have a set of variables called V, which are independent factors which affect X independently among themselves, and there's a dependent sort of variables, that is W, which are dependent, so we cannot do anything about them in some sense.
So could you please repeat?
So
you have X.
You have X.
X has been generated from
two different sort of factors. One is V, one is W. Now these set of factors, V, they are independent among themselves. These set of factors W are dependent in some sense, right? So now what they say is, okay, so if you want to model something like this, right? So their intuition here is that this, if I, so now since we don't have the actual model prior with us, the idea is that, okay, we will now approximate using some sort of posterior, right? And the reasoning of why should we add a constraint on this posterior with DKL of P of Z less than C is to capture these independent factors, right? That's the intuition that they have provided. So by setting this to N0I, what we are trying to do is we're trying to say, okay, try to make this Z as independent possible, so that they'll be able to capture V as much as possible. W, it won't be able to capture, and we are fine with it. And that way,
if you are able to capture V, you are in a way getting information about W also, because W is dependent on V.
Dependent among itself on V. On V also it can be, but but they don't mention that.
Okay. So in other words, W is containing some information, some independent information.
Some information, yes, from V, yes, correct. Yeah. So, so hence the idea that, okay, so putting this sort of constraint makes sense in that way. So they bring this sort of idea into this constraint. Why should we have this constraint over the posterior, right? That is because you want to capture independent factors which are generating X.
But there are also other set of parameters which are generating X, which are fine independent, but they are also containing some information.
Some information about X will be lost. Yes. Okay. They're saying that we want to capture V in the first, basically. Again, so this also relates to an idea called disentangling factors.
Okay.
So the idea is you want to find out factors which are disentangled among themselves, as much as possible.
Right.
So in that spirit, this makes sense. That's how they intuit this process.
Right. So I was thinking one possible thing could be X is a random variable of some high dimensional, let us say D dimensional.
Right.
So this can be broken down into many such dimensions. For example, in which we are independent. So rank of the covariance matrix of X is V. And the others are only dependent, so therefore you don't need that information.
Correct. So that would be in case W is completely dependent on V.
But you're saying also
possibility that W is independent of V. That is the way I read it, at least that made sense to me. So yeah.
So
capture these independent factors only. Okay, so hence they bring up this idea, and then they talk about this Lagrange multipliers. So we'll just complete the discussion last time what we were talking about Lagrange multipliers. So the idea here is that, let's say we have a unconstrained problem. If I want to minimize over, let's say, some f naught of x, in case I have some conditions to be fulfilled for the solution that I want to find. For example, let's say fi of x less than 0, hi of x equal to 0, some m inequality constraints and n equality constraints, then it's called the constraint optimization problem. So now the idea of Lagrange multipliers is that you build something called a Lagrange function, which is of this form where you have f naught of x, some lambda multipliers which multiply this function fi of x and nu I with for hi of x, right? And this lambda is now a vector of all the lambda 1 to lambda m, and nu is basically a vector of nu 1 to nu m. So now what we can so the way we proceed here is the fact that we get a function called as g of lambda comma nu. This is calculated as a minimization of this Lagrange function over x, and then you find the maximizing parameters of g of lambda comma nu. So with this condition, the lambda has to be greater than 0, and nu can be unrestricted. So we'll see why this idea. So so let's say I have something like this, minimizing f naught of x such that fi of x less than 0. So let x star be an optimal solution of this, right? So optimal solution will also be a feasible solution. That is, it basically it satisfies all the constraints, and let the optimal value be p star. So f naught of x star is p star, and let x bar be some feasible solution. So now, and since we only have inequality constraints, we can always.
So x bar is what feasible solution.
Some feasible solution.
So x star is an optimal solution.
Correct.
So feasible means like there will be many feasible solutions.
Yes.
Okay.
So
but
feasible.
Optimal will be one.
Optimal will be one. Okay. Yeah. So feasible is no. Optimal also can be multiple, but the value of the optimal is same all the points. That's why multiple optimals can exist.
Okay, fine.
It's also possible. So here x bar is a feasible solution. So what this means is that it satisfies all the constraints.
I see. But it need not be optimal.
Optimal, right?
Understood.
So
basically, the range of values of x that the function may take.
Correct, exactly. So which solves all these things, right? So we build the Lagrange function like this, that is f naught of x plus this idea. So now g of lambda will be taken as minimum over x of L of x comma lambda, as we discussed. So now here, so for all x prime, whatever x prime is x bar is a feasible solution, fi of x bar is less than 0. We know this, right? Now let lambda I be greater than or equal to 0 for all I. So then we can see that L of x bar comma lambda will be less than f naught of x bar, right? Because we have here f naught of x, and this is what is being added to f naught of x. So if I have an x bar here, since this is negative, this is positive, so it will always be less than f naught of x bar for any lambda you choose, as long as lambda is greater than 0, right? Then, so which means g of lambda will also be less than f naught of x bar, right? Because g of lambda is the minimum over these values, so this is also going to be true. And since it's true for all x bar, it'll be true for x star also, right? Because it's also a part of the feasible set. So g of lambda is less than f naught of x star. F naught of x star is given as p star, right? So now what we're doing is we are trying to maximize a lower bound on this p star, right? So we have lower bounded the optimal value with a function.
So
increase the lower bound as much as possible. So now the lower bound, if I find the maximum, let's say its value is d star. So this d star is called the dual solution, and p star is called primal solution.
Dual means what?
So because we have cast the problem into a different statement now, right? Because we are now looking at a maximization over this g of lambda. So this is called a dual problem of this primal problem, right? So this is a primal problem, that is this is a primal problem, and the dual problem is this, basically maximizing lambda greater than or equal to 0 of g of lambda,
Right.
where g of lambda is defined as minimization over x, L of x.
Also there. In this problem
we are not taking, and we'll see it does very similar sort of ideas will flow through. So the idea is that, okay, so we have a dual solution. So basically it is let's say the lambda at which this dual solution is obtained is, let's say, lambda star. So we'll call the g of lambda star as d star, right? So this d star is a lower bound on p star, right? So and now let's say we were to do something like this first. So instead of first minimizing over x, I'll first maximize over lambda, right? So my claim is that this is equal to f naught of x if x belongs to the set of feasible solutions, infinity otherwise. So why would this be?
If lambda greater than equal to 0, so what? Maximum of this infinity otherwise.
Just as a reminder, so
because we like the new problem was plus lambda times something.
Correct.
Yeah.
So sorry. So we said this is a problem now. I equal to 1 to m lambda I fi of x, right? So basically, see if
so maximum is over what?
Over lambda.
Over lambda.
Huh.
So you are saying if the function is outside that range, the maximum value would be infinity.
Infinity.
Like infinity because like we can take any value of lambda, which can also be infinite. Therefore, like this.
Correct. Yeah. That's it. So the idea is if any one of the lambdas is infinite, so this will be infinite, right? But that is only if x is not in the x prime set, right?
If x is inside there, then also I can put lambda equals to infinite and.
But it will be upper bounded by this value, no? That's the maximum where it can achieve.
Oh, okay.
Right. That's the idea. So basically, let's say there's a x tilde which does not belong to x prime set. Okay. So that means it's violating at least one constraint. Okay. So let's say the jth constraint is violating, which means fj of x is greater than or equal to 0. Sorry, greater than 0, not strictly violating. Yeah. Greater than 0. Right. So what I can do, I can take this lambda j to infinity and I can make L of x comma lambda to go to infinity. Right. That is the argument for this part. Now, if it is satisfying all the conditions, right? So how much ever I take this lambda high, right? It will always be bounded by the f naught of x, right? Because for every x bar, for all x bar, lambda I fi of x bar is negative. Right. So this sum will be negative. So the maximum that this sum can achieve, this L of x comma lambda can achieve, will be f naught of x. Right. That's the idea. Right. This is the point. So hence.
Because the minimum value of this can be 0.
Of this can be 0.
Therefore, the
maximum is this one. And yes. So generally we don't use max and all. We use inf and sup, because it's possible that it's not achievable in all of those sort of issues. So but the idea is this. So let's say it's all achievable and everything. So the maximum it can take now becomes 0, and therefore f naught of x will be the maximum it can achieve if it belongs to the x prime set. So therefore, and now, so let's say this is what I have function with me, right? Now if I were to minimize over x, right? Now because it's infinity, right? The minimum of this will just be the minimum of f naught of x, right? So therefore, minimum over x of maximizing of this quantity is equal to minimizing over f naught of x, which is nothing but p star, right? That's exactly what we got. So we are saying that this was the dual solution, right? Just we saw before, this was our g of lambda. And you're saying that if you maximize this lambda over g of lambda, I get d star. This is our p star, right? So under some conditions of something called as KKT conditions and etc. So we can show that d star is equal to p star, right? So hence the idea is if we were to if we want to minimize the unconstrained problem, constraint problem, we can construct a Lagrangian and first minimize the Lagrangian over x and then maximize over the Lagrangian multipliers parameters. So on the same thought process.
Equal to p star, all the inequality constraints are
exactly satisfied. Right.
So in that condition, D star equal to P star.
D star equal to P star. It'll be lower bound on P star. Yeah. It'll never cross P star. Yeah. That's the idea. Right. So yeah, so this is the ideas on this is the idea of Lagrange multipliers. So hence, because we have a constraint here, that constraint gets broken down like this. So basically, I'm taking this Lagrange becomes expectation of this. This we want to maximize minus some multiplier, that is beta, into the constraint that we have. The constraint is this. DKL is minus C less minus C, and then if you were to make it a bit solve it, you will get plus beta C, which doesn't depend on parameters at all. So this is exactly what we want to do. So we'll try to maximize this quantity with respect to our usual elbow function. Right, and we saw all this last class. That is, original VAE can be seen as beta VAE with beta equal to 1, and the ideas on why beta would affect the inference and so on. The last thing that was there was a novel way to train, and the idea is very similar to what we discussed, what you said last time. So the idea is that what we do is we have the Lagrangian, right? So we have z given x log p theta of x given z minus, let's say, some gamma and some sort of a KL minus some c, right? So what they do is you start with a low value of c. Okay, you start with the low value of c and train this model, right? So what we are giving the model to do, we're saying, okay, try to reconstruct as best as possible with whatever dependent factors also, we are fine. So we're giving it some sort of a more sort of a leeway in the initial, right? So once you train this, then you decrease some c, and then again train, and you keep on decreasing, and you keep on decreasing. So the idea here is you keep making how much you want your factors to be independent, keep on increasing that sort of a strength of the constraint, while trying to make sure that you don't lose out on the accuracy. Because last time, as we discussed, they saw that they had a lower reconstruction accuracy. So here they were able to regain to a good level, right? Because initially the idea is that the decoder and all of, they have learned good enough information to be able to reconstruct the data, and then we keep posing constraints, etc., over training iterations. That's the idea.
In a way of like stepwise learning.
Stepwise learning, correct.
So you first have a better reconstruction,
right?
Loss, and then like after that you try to.
You keep on making it independent sort of factors. You force the model to learn independent factors later on. First, you try to fix the reconstruction.
So this is what the reconstruction loss. The second one was what? Some name was there.
This one.
Second one.
These are regularization term basically, right? Because we're trying to impose a constraint on the latent space.
Understood. So I'm asking like when we put beta equals to 1 in that original expression,
right?
We got that the first term is related to reconstruction,
right?
The second term is the how well you're able to like find the latents. So we named it something, no?
Is it? We call it something.
Okay,
so this should be here. This should be here.
Okay.
Because this is where we dissected the elbow altogether. So so we haven't called it anything yet. So it's just that, yeah. So basically, this is just like giving some sort of a constraint on the priors that you're learning.
Yeah.
That's it. That's the thing that we want to constrain, and it's done by using a Gaussian distribution. So this could be seen as a regularization parameter over the space, latent space, right? Okay, fine. So this is the idea of beta VAE. Then another paper by some other authors, they gave this idea of something called info VAE. So what they do here is first they prove, they intuit one very basic sort of a concept here. So let's say we have elbow this is our elbow, usual expectation over overall data of the elbow for each data point. And if you put all those terms here and rearrange some terms, you will get something like this. So you get a KL between the model probabilities and your actual probabilities, right? Then the model approximate posterior and the model posterior, and some sort of entropy term of your actual data, which doesn't depend on any parameters, neither theta neither phi. So again, so very simply, thought process is, if this DKL is 0, if this DKL is 0, it means we have matched both the actual data distribution and the posteriors, right? So we are in the very good possible thing, and which makes sense also, because we're trying to maximize elbow, which means you want to minimize this term and this term also, right? All well and good here, and we don't care about this term at all anyway. It doesn't depend on anything. We can't control it anyway. So so now let's say we have this p theta, right, of dot given z, yani ki your decoder, right? Because it takes your z, constructs x whatever, right, from z. Yeah, basically whatever parameter. So in our case, it's x, whatever we construct, right? So so let's say this family, yani ki theta belong to some cap theta. So let's say if it is sufficiently flexible. So by flexible here, they mean some sort of like very powerful. You're able to match any sort of distribution, right? So
any distribution, they have the
possibility of explaining, right? So let theta star be such that theta star of x given z is equal to px of x for all x, right? Means you're able to match the distribution ekdam precisely. So if that happens, then p theta star of x can be seen as, again, this is just breaking down into latent and this one. And as we said, p theta star of x given z is equal to px of x from this particular equation. So this can be seen as just px of x, because this becomes integral over this quantity, which is 1. So p theta star of x is equal to px of x, right? Which means that the first term is 0. Because the first term was px of x, px and p theta, right? So we are able to model the complete distribution exam precisely, right? Next, now we are seeing that this p theta star of dot given z is same for all z, right? Because this doesn't depend on z at all, on the RHS side, right? So whatever z I give, it will be able to reconstruct, give my actual this one. So which means that p theta star of z given x is now equal to p of z, because x and z are independent, right? So independent, it will be equal to p of z, right? So and basically p of z, we know we generally have a simple distribution like Gaussian distribution or whatever, right? So now what I can do is I can choose some phi. Phi is basically our encoder parameters, such that for any x, just give me p of z.
Just give me p of z.
Right?
Okay.
Hana? Because so for example, let's say if you want to model a distribution, what I can do is I can set these 5 parameters such that ignore whatever x gives me, just keep on getting me data in terms of Gaussian distribution, right? I can do that using parameters 5, right? So if I do that, second term also goes to 0, right? So what has happened? This term goes to 0, which means you have achieved the maximum possible elbow, right? And we have achieved that without using any latents, right? Because anywhere, if you see, what happened here, right? The model is not caring about z at all. Right. Just because the fact that we have a very powerful decoder. The decoder was so flexible and so powerful, such that it doesn't need information from z. Rather, it is just able to generate all your points very strongly. Okay. If that happens, in a way, what's happening is your elbow is getting maximized. So your objective function will get maximized, but you will not have any useful latents out of it. So
in a way, if we see that given that it's able to like reproduce the exact x, it must be having some good z. It's also possible that Z is not a latent noun. It's like having all information that is possible because of which it's able to reconstruct.
All information which is able to reconstruct.
Yeah. So it's not a. Okay, fine.
Yeah. So yeah, correct. Because this particular line, that's what it means in some sense, right? We're saying that information from Z is not required for the decoder to be able to construct X.
Yeah.
Right? So we're saying in some sense here. This is what we are. This is what we're saying. So it could either contain all information about X, right? No. If it contains all information about X, then this term won't be right.
Why would it not be right? Because we are assuming. Okay. So no. Okay, so I got your intention. So you're saying this term won't be correct because then Z and X won't be independent.
They'll be purely dependent.
Purely dependent.
Purely dependent, right? So, yeah, correct.
But wait, how can Z be independent of X?
So if you have a powerful decoder, that's what it turns out to be. That's the idea is they're trying to sell. And actually speaking, this intuition we should have got a bit before also. Let me bring that here. So we discussed something here, if I'm not wrong. Yes, here.
See, okay. So Z is only a linear combination of X, right? Okay, not linear, but non-linear group.
Correct.
So how can Z be independent of X? Or is it only like in theory?
You're saying that this is happening only in theory, this sort of thing.
Yeah, correct. Yeah.
Yes, because getting
this trying to like approach it as like much as possible.
As much as possible, in some sense. So we are saying that okay, this decoder is very powerful. Now, very powerful decoder, very flexible decoder. I don't know how to. I understand this also. So ideally speaking, it's. Okay. I got how to understand this. Okay, one second, wait. So let's say we have we have Z to X. This is what we want to learn, right? Let's say, okay. Sure. So there's a Gaussian distribution, and X is some from Px of X, right? Some unknown distribution. Now, let's say it learned, so it's able to learn this perfectly. What the decoder, right? So there was and we know that there exists a function like this, right? And let's say that theta or decoder could learn this function ekdam perfectly, right? So if that happens, right, what should the encoder output for Q of Z given X? Will it matter to the decoder? That's the question. It will not matter, right? Because it's you give Z, it's able to construct X, it's able to construct Px completely, right? So in this particular scenario, so which means that your decoder is very powerful, right? It's able to map from N01 to Px completely. So if it does that, whatever the encoder outputs, it doesn't care. It will take Z, it'll construct X. Yes. Why could something like this happen? Is that your point?
To some extent, yes. Or in other words, you give me anything, I will output a dog. Like a distribution of dogs.
Correct. So yes, so we're asking you to learn a distribution of dogs.
Right.
We are not wrong there.
Right.
Yeah. Now, the decoder is such that it's able to map any N01 image to a dog image.
Okay. Which is possible.
Which is possible.
Yeah.
Right. Yeah. Now, so then the question comes, this encoder is, we don't need this encoder anymore.
We don't need, correct.
Ideally speaking, we don't need encoder anymore. You pass Z, you'll get all dogs images, right? That's the idea. That's the idea, right? So hence this flexible idea, I think powerful thing comes here.
So powerful that like
it's able to it has learned that transformation, that function transformation so strongly that I don't need any more information from the encode. I'm done. I don't care about it, right? That's the idea. Okay. So basically, this can be seen as, so decoder learned the function transformation perfectly. Right. So if that happens, ideally speaking, your encoder need not do anything other than just outputting P of Z, and this it will do. Right. It's not useful, and it will do that because we have a DKL term, right, which tries to match these two. So it'll just try to output Gaussian variables, right? So now, so we are happy that the encoder could do all of this, but the point is, we wanted, so one aim we discussed that we want generation and all of that. The second aim of inference starts failing here, right? Because if you're hoping that your encoder will give you a meaningful distribution over Z, which you can use as your approximate posterior, that will fail. So here, the issue here is your inference procedure starts failing. So let's say if you want to use it for some downstream task, you cannot, because it's just going to be give a random sample from N0I. So hence, so to solve this inference issue, very simply, the idea is that so we have a term called mutual information, right? So mutual information can be so we discussed what entropy is long time back. So it can be seen something like this, right? Expectation of the log of the probabilities over the probabilities. A conditional entropy is similar to this sort of an idea, where we try to map the conditional distribution, right, over this P here is a joint between X and Y, right? So, and mutual information is taken as the difference between these two terms, right? And again, can be shown to be equal to this sort of a distribution. Again, we know that DKL is greater than 0. So mutual information basically is something non-negative. And here the idea is that if the mutual information is 0, which means these two distributions are equal, right? That means I can write P of X comma Y equal to P of X into P of Y, which means that by definition, X and Y are independent, right? And vice versa. So basically, if I have if I is 0, it means X and Y are independent, and if and vice versa. That is, if I don't have this one. So here the idea is that, so as we saw, what ended up happening was that we found a Z which was independent of X. That is where the inference procedure failed. So then what the authors do is they write this elbow in another form. This is one more form of writing the same elbow. So here you might see some new terms. So this is called as Q phi of Z and Q phi of X given Z. Till now we have seen the other way. So what they define is, they define this new distribution called Q phi of X comma Z, a joint distribution between X and Z, but which is formalized in this form, which is the posterior distribution multiplied with the actual true distribution. And Q phi of Z can now be seen as a marginal over this distribution, and Q phi of X given Z is just the using the Bayes theorem, you'll get you'll get this term. So Q phi of Z given X into Px of X divided by this integral over this one, right? So now what we do is, we will force the model to capture information about X in Z. So that is through mutual information. So what they do is, they ended up adding a mutual information term, which with Q distribution, that is Q of X comma Z as a distribution. So which can be seen as this joint distribution and the respective in the marginal distributions. So now the elbow, if you they use this particular formulation and they write it in this form. So with lambda as a parameter here, q phi of z and p of z. This term is again from the above term, and they use an alpha term with this iq of z x comma z. So because we are maximizing elbow, which means we are maximizing this term also, which means we want to maximize the mutual information. That is, we are forcing z to capture information about x. Then if you write it down again into our the terms that we remember, that we know, this is our term that we have, the deconstruction term, q phi of x given z log p theta of x given z, right? This is the term which we have to regularize your latent posterior and your model prior, right? And then we have a new term, which is q phi of z and p of z, its DKL distribution. So what is q phi of z? Again, we can see this to be something like this. Interior marginal relation over x of this distribution, which can be broken down like this, and which can be seen as an expectation of this quantity, right? So basically, there is no closed form for this distribution. Unlike here, we lucked out, right? We had a closed form formulation here. So here we don't have a closed form for this sort of a method. So one approach is that we can end up sampling from this distribution and do all of that sort of thing. Other approach is proposed to be adversarial learning, which we will probably discuss in next class or next to next class. So how do you solve this particular term? How do we get gradients and etc. from this particular term? That will be done going forward. Okay, this is the idea of info VAE. So basically, the word info because they're using mutual information. That's the idea. So we saw two ideas. One is in beta VAE, that is you want to learn latents which are more sort of independent of each other, and we saw that that may not always be good enough. Info VAE sort of builds upon the idea that it's possible that you will learn latents which are completely independent but no use in inference mainly, and hence we want to enforce that idea here. Then we have an idea called as something called as VAE with VAMP prior. So VAMP prior. So one basic assumption that the authors of this paper challenge is, why should the prior P of Z that we have should be N0I, right? So one idea why we wanted it to be is because for simple sampling, right? Sampling becomes easier, right? Because what we are forcing through the DKL term, we force that all your latent posteriors are equal to P of Z, so that when I sample from P of Z, I can get my X, P of X, right, passed through the decoder. So now the idea is that, okay, we'll parameterize this prior by some parameters lambda, right? So now your F theta of Q of Z given X becomes a function of the lambda parameter also, which can now be seen as something like this, right? So instead of P of Z, we have P lambda of Z. Simple, straightforward idea. And that you can break it down going forward and you will get something like this term. So just expand DKL term in its expectation of Z given X and so on. So now the question is, how do you find what is optimal prior is, right? So any thoughts? How would you solve this problem? So think of it as any usual problem for optimization, right? So how do we go about doing that?
We take a derivative.
Derivative and all that we want to do, right? So first thing we need to note is that this is for a single data point.
Right.
So we'll first, take expectation over this whole quantity, right? So, and then again, one simple idea here is that all of this doesn't depend on lambda at all, right? These two terms. It's only this third term that depends on lambda. So I'll try to, for now, I want P lambda star. So I can just look at this term, right? So basically, expectation over Px, expectation over Q phi of Z given X, right? And log P lambda of Z, right? This is what I want to maximize. So I want to maximize this with respect to P lambda, right? I want to find the optimal P lambda, right? So basically, now what ended up happening is, so if you think about it, what are we trying to do? This is a function of P lambda, right? So it's a, let's say I call it J, some auto optimization, this one. So this is a function of P lambda. P lambda itself is a function of something.
The function of P lambda.
And P lambda is a function again.
Yeah.
Right, yeah. Which maps Z space to some positive real number, right? So this sort of optimization is this J is then something called as a functional, right? So basically what we need something like which gives us dou J by dou P lambda sort of a thing, right? So we want to take a derivative of something with respect to a function. Now this usual calculus doesn't apply to this. So we have something called as Euler-Lagrange equations. So some idea about this. So basically, let's say I have a function, let's say J, which is defined in this form, a to b some L of some functions dx, right? So here the idea is I want to find a function f which extremizes J, maximizes or minimizes, we don't know. So some sort of point where it goes to 0, right? So it could be either minimizing or maximizing. Okay. So now let's say, so basically this idea that I want to find a function f. So because J depends on the function f through this L and over integral, right? So such form of problems are solved using these Euler-Lagrange equations. Again, we'll not go about derivation, but what it is that function f, whatever you want to find or whatever, has to satisfy this equation. This is called the Euler-Lagrange equation. So this has to be satisfied by the optimal f, right? So basically, if you run this equal to 0, you will get some f. That f will be equal to f star. That's the idea, right? So this sort of idea will apply it here in VAE with Ram prior, right? Because now what I can do is I can write this this J as, right, integral over x, integral over z, right, log p lambda of z into this distribution q phi of z given x, this distribution px of x, right, dz dx, right? Now then we already saw in the previous this one that I can write this as something like a q phi of x comma z, some new joint distribution, and then I can put this x inside this, right? So I will have integral z log p lambda of z into this integral x q phi of x comma z dx dz, right? And this we know just turns out to be, again we have defined these terms just now, so this becomes just q phi of z, right, aggregated in some sense, right? Dz. Now one question, so now we can basically apply the Euler-Lagrange equation in this form, right? So the point is okay, but is this enough? If I apply dou J by dou P lambda and all of that sort of things here, so and solve this equation, is this enough? Is there anything else do we need to do?
So so your question is like, if I do dou J by dou lambda, will I get an optimal solution or not for lambda?
For lambda, for P lambda.
Yeah. So which I think we get.
No. So there's something special about P lambda which needs to be still put in this.
The constraint that P lambda are greater than 0.
Greater than 0? Is that enough?
Okay. In the constraint, like the integral of P lambda z should be equal to.
Should be 1. Okay. Right. Because
we are differentiating probabilities now.
Probabilities, so we need the constraint. So under the constraint that, sorry.
Another constraint of Q phi Z should be greater than 0 and Q phi Z should be like.
No, but that is already here, no? See, Q phi of Z given X is a Gaussian distribution we have taken. Px of X is again non-zero. So this is going to be non-zero distribution and all of that, right? So here, see, here the point was we want a optimal P lambda, right? But because, so if I just solve for this equation, I will get any P lambdas.
Which will not even satisfy
your usual, probability distribution constraints. So we need to apply this constraint, right? Equal to 1. Now this, we know how to deal with constraints. Lagrange multipliers, right? So put just j equal to, so your final j sort of becomes something like this: P lambda of Z, Q phi of Z, minus, let's say, or plus, let's say, beta P lambda of Z minus 1 dz. Right? This becomes your, this is your, in the Lagrange equation, this becomes L of your Z, P lambda of Z, and P lambda prime of Z. There's no P lambda prime of Z, so that term will go to 0. So you can just try, so take it as an exercise. So try proving this. So basically we need to do something like this. So so we need dou L by dou P lambda is equal to 0. So now we can apply it. This is L. P lambda prime, there's no term here, so that becomes 0. The whole term goes away. We just have very simple dou L by dou P lambda equal to 0. Now basically how do you do this differentiation? Just consider P lambda as a variable. Right, so that variable, so this is that variable, this is a variable. Simply apply this, you will get some P lambda, and you will be able to solve for this beta. All of that, apply constraints again, you'll get some P lambda. Right, so at the end it turns out to be something like this, right? Expectation over Q phi of Z log P lambda with this constraint. So if you do that, you will get P lambda star to be this sort of a thing, right? So basically we're saying that the optimal prior is the average over all these postulates that we got for every X that we have in a data set, right? For all X, because I'm taking Xi to Xn, all possible. Which makes sense, right? This is very obvious sort of things that came out.
So just input all X's. And whatever, say, the distribution of Z you are getting, based on that you are getting a prior.
That's the prior. So if you sample from that, you will be able to do better. Right. That's the idea, right? So you will sample from this P lambda of Z when you generate, right? You will sample from this and pass it to a decoder. You will get this one.
So we started by saying that this particular formulation assumes that. So the problem, why did the paper start? It said that this particular something assumes the normal distribution.
Correct.
So for P of Z, you are assuming a normal distribution.
Correct.
So this says you need not assume a normal distribution as prior, but rather you can compute the prior
by doing this. Right. Okay. Exactly. So one aside, so this sort of is similar to something that we have already covered. Some sort of a distribution family this is, if you think about it. Anything comes to mind when you look at like this?
So if we assume that Q phi Z given X, Xi, particular Xi, belongs to a Gaussian, then this summation would be a mixture of Gaussians.
That's it, right? So similar to this, basically a Gaussian mixture model.
Yeah.
Very simple, right? So this basically turns out to be, if I write like this, 1 by n Q phi of Z given Xi, right? And this.
But again, based on the assumption that Q phi Z given Xi belongs
is Gaussian. Yes. That assumption we have. This is n of Z, mu phi of Xi, sigma phi of Xi. Yeah.
So which this paper doesn't.
Which?
This assumption. Or
no, this assumption is there. This assumption is fine.
But the assumption regarding
The prior. Only that. Okay. Yes. So they're tackling this only the prior assumption that we had in this paper. Yeah.
So do some work. Like one more paper on like
done. Yes, yes. So many variations have come out. Many variations have come out.
See, for this also you can do the same thing. Like,
yes, yes. So why should this be Gaussian?
Exactly.
Right.
And if you can like prove that this is an optimal for that prior,
some solution will come. Yes, yes. In that way. Yes, correct. So this, yeah. So this turns out to be some sort of a n component Gaussian model, right? And where each component pi I, your prior probabilities is 1 by n, right? This is how we define this, right? So I equal to 1 to n pi I with some Gaussian distribution, right? That's the idea. Now, so they come to this and they say, okay, yeah, this is what the optimal is and all of that. But the problem is that this gives you computational issues. Now, think about it. So let's say if I want to sample in real time, I mean, so, okay, I trained everything and everything happily done, right? And I want to sample from this VAE, right? So how will you sample? It's a GMM. We know how to sample from GMMs, right? So first you choose a component with 1 by n again. So basically, it's equal to saying choose one sample from the data set, and for that sample you run through your encoder, right? And you'll get some Z. That Z is what you will pass to a decoder and get this one back, right? So now, if you think about it, what will happen is you will need to save all of your training data, right? All XN have to be stored, right? So all data needs to be stored. That is point number 1, right? That becomes a computationally challenging point. That is one. Second thing is while training also, by the way, right? Because what will happen if you want to train this model, at the end of the day, you have to calculate this KL term or this term, whatever, right? This again, the whole idea is log p lambda. If you want to do, you have to go through the whole data set again, get all of those samples, and then pass through your encoder. Very computationally expensive, right? That's the problem.
Because for each iteration you have to do that.
Yes, each iteration you have to go through the whole data set. So which is very problematic, right? So sampling is an issue because you need to show all data, and for every iteration, go through the whole data.
Right.
Go through whole data. So this is something that we don't want to do, right? That's point number 1. Point number 2, it's also overfitting, right? Why? Because if you think about it, what are we doing in this Gaussian model, right? We have n data points from training. You choose that one point from the training data set. You pass it through the decoder. You will get a Z. That Z will contain information about that data point.
Right.
That data point you'll take that Z and get again pass it through a decoder to get some X. That X will be same as this X only, ideally speaking, under a very well trained this one. So in a way, it's overfitted on your training data, right? So we don't get any new samples if we do this sort of a thing, right? This is one. And on the contrary, if I use P of Z equal to N0I, it is not at all overfitted, right? It is very, in some sense, that is underfitting in some sense. Or you can say like it's a very strong constraint on your Q5 of Z given X, right? You're asking for every X you have to be equal to that Gaussian distribution, right? So on the flip side, this is very sort of constrained, right? That is the problem here, right? So we need some sort of a middle ground. So how do we solve this? No, they gave in same paper only. So in this, what they told is they give something called as pseudo inputs, right? So what they do is they have something called as UKs, okay, and these are learnable parameters, learnable vectors in some sense. So UK is going to be actually a vector in the d-dimensional space, which is the same space and where your X lies, by the way, right? Now, what we do is we have these UKs are learnable. So you start with some random value. You want to keep training those from your data, whatever it comes down. The biggest idea here is the form of P lambda is the same, right? The form as we saw previously, it's exactly the same, right? So instead of going through all data, you pass through only some of these few this one, and make sure you choose k less than n because you want to be computationally tractable, right? So so with this idea, they give this idea called the P lambda of z. That is your optimal prior. So what you do, and then again, the idea is simple. Your UK, every UK is a learnable vector. So at the end of the day, you will, when you do your elbow, you need to look at the elbow, dou L by dou elbow, whatever, dou UK. Okay. Right? That's how you'll update all the UKs, and you will use that to generate. And again, the way to generate is simple. Again, this can be seen as a Gaussian mixture model. So choose any one of the inputs, pseudo inputs, get a Z, and get from that Z you get your output from your decoder. That's the way you will sample here, right? Clear? Yeah. This is exactly what it is. And keep updating UK also. Correct. You keep updating UK throughout your training procedure. That's the idea, right? So in some sense, like learnable inputs. Right. That's the idea here. And it's called why it's called VAM prior, because it's called variational mixture of posteriors, okay. Right? Because it's a posteriors and mixture, and it's a variational because this is an approximate posterior. That's the idea. That's how they've named it. So if you go through the actual paper, they have a bit different way to arrive at this, but again, similar sort of thought process, right? Okay. Any questions? Right. So now we'll go to the last variant that we have in VAs. So here, something called as VQ VAs. So there, so we have one core assumption that is being challenged in this paper also. That is, why should the latents be a continuous random variables, right? Why can't we use a some sort of a discrete random variable for the latent? Okay. And it's inspired by the vector quantization idea. So basically, in a big sort of idea, vector quantization is basically you want to find a representative for a set of vectors. So you're basically quantizing the vectors in some sense, right? So there are several ideas in this paper. We'll go through one by one. So first thing is you choose some sort of k representative vectors, right? Each of dimension d, right? So your latent embedding space is to be this R k cross t. Okay. So where the latent, that is z, is a discrete variable which tells you which embedding vector you will choose. Okay. Okay. So yours to generate whatever, we'll come to that. Right. So z is a latent discrete latent variable which takes 1 to k values, one not sort of thing. And what the idea, the point of this z is it will tell you which embedding vector you should choose from these k representative vectors, right? Then, so how does the procedure go about here? Is basically we go ahead something like this. So we have x, it goes to the encoder, your phi, and gives you an output ze of x. That ze of x is quantized with respect to all your embedding vectors. So basically choose the vector to which it's closest to. Again, using Euclidean distance. This is the VQ operation, basically quantizing that in a set of possible vectors. ZQ of x is EK, and that ZQ is then passed to the decoder to give x, right? So encoder is giving ZE, pass it through an argument operation, and then you will get ZQ. That ZQ is passed through a decoder to get x. This is the idea, flow of the problem. Now, under this sort of thought process, what will happen to the posterior that we have? Okay, so your Q phi of, again, Q phi is now a distribution over a discrete set of values. So Q phi of z equal to k given x will now be equal to 1 for whenever the k is this, the minimizing, this one, otherwise it's 0, right? So basically, is there any randomness in Q phi of Q phi anymore? if I give an x, right? If I give an x, is q phi the distribution over z? Is it random or no? There's no randomness at all, right? It's a deterministic mapping in some sense, right? It's completely deterministic. So then what they do is, let's say you define a prior, uniform prior over all k, right? Equal to 1 by k. So then you can.
Now you have made it like not deterministic.
Not deterministic, actually, flexible. Very flexible. So now, what happens is the DKL term. Previously, DKL term became computable everything because we assume P of Z to be Gaussian, Q phi to be Gaussian, and therefore we had a closed form, all of that. So because now the whole paradigm has shifted, we need to recompute DKL, right? So how do we compute this DKL? This can be seen as, again, from the definition, expectation over q phi of z, q phi of z given x, log of q phi of z given x by p of z. This is the discrete distribution. So expectation now becomes summation, right? Over all possible values that z can take, right? So log of z equal to j, p of z equal to j, q phi of z equal to j, and all of that. Now, let's for a moment assume that q phi of z given is some sort of a probability distribution, but it's a very hard, like one hot sort of a distribution, right? So its support of this distribution will be only where k is the minimizing, right? Remaining everywhere it is 0, right? So all of these terms, okay, will become valid only when q z equal to k, right? The minimizing one. So this summation turns out to be just one term. That term is whenever equal to k, right? And we know what this value is also, by the way, right? This is 1, right, for that particular k. So this becomes 1 into, this is again 1, this is a uniform prior, 1 by k, so it becomes log k. So there is nothing in DKL which is random, point number 1. Point number 2, no depends on the parameters also. Nothing from phi, nothing from theta, nothing came out here, right? So DKL term basically turned out to be just a constant, right? So all derivatives with respect to DKL term just go away, right? So we just have one term, that is the reconstruction term, right? Now, previously we had this issue of gradients, right? Because there we had an issue that, okay, if q phi of z given us is a multivariate distribution whose mean and variance depend on phi, so how do I pass the gradients if I sample, right? So here what will happen, right? So if you think about it, when I get when I want to update this encoder phi from this reconstruction term, right? There is this argmin operation. Argmin operation is not differentiable, right, by default, right? So then what to do, right? How do we solve this problem? Any thoughts? So it's first of all not even continuous in some sense, no? Because whenever the value shifts, it just sharp sort of change. So therefore, it's not even differentiable, right? So that's the issue. So minimizing, maximizing options are not differentiable in general, right? So that's the problem.
So now what's the question now?
So
how will you update the parameter phi?
Parameter phi, right? Because previously we had this issue. We had an issue how to update encoder. We use a reparameterization trick, right? Where we parameterize as the random part in something else, derivative part in something else, and we could pass the gradients very nicely. So now what to do, right? That's the question. So, so for this sort of issue, there's something called as subgradients, something etc. exist. But what the authors have done is very sly sort of an approach. So this is the flow, right? X gives ZE of X, which gets transformed to ZQ of X. I mean, with the minimization operation, right? You get a ZQ of X. The ZQ of X passed through your decoder gives you X, right? Now, ZE of X and ZQ of X are in the same parameter, same dimension space, right? At the end of the day, right? So what they do is they just copy the gradients from here to here. So what they will do is they will find out the gradient with respect to ZQ of X, then just apply those gradients at this layer and then backpropagate. That's it. Okay. So and they said that so the right way to solve, I mean, right in the sense, more mathematical way to solve it is using something called as subgradients. But they say that this worked well for them in practice. So gradients copy worked for them. So that's how they solved the gradient problem that we had in usual VAE. Right. So now, okay. So so all of this is fine, but one thing that we haven't talked about till now is this embedding space, right? Because we said, okay, there is an embedding space, but we need to find what the embedding space is and etc. So what the authors did is they added two terms for your loss function, right? So let's look at this. So first of all, the expectation here went away, right? Because it was a deterministic quantity. So whatever, so we had x given z here, right? So that z is basically zq of x, right? Zq of x passed into the decoder gives me x. That's my log of p theta, this one. So this part updates the decoder. Simple and straightforward. Now, then what they do is they add this term called as this encoder output, and this E is your embedding layer that you have, right? So basically, this again based on to the idea of vector quantization. The idea is you want to make embeddings as close as possible to the encoder outputs, right? So this SG basically stands for something called a stop gradient. So what we're saying here is so stop gradient in general, I mean, what it intuitively does is saying when you're updating E, don't update encoder at that time. So update one by one. When you're updating encoder, keep this constant, don't do anything to it, and update whatever you want to do. So basically what will happen is, because of this, these embedding layers, vectors, whatever you have, they will start going closer and closer to the encoder output. Right, and which is what you actually also want also, right? Because you're saying that ZE of x is something that is mapping your x to some space, right? So if your embedding vectors are in that space, it'll be much more better in that sense, right? And it's also a result of your VQ operation, vector quantization operation. So embeddings will get updated using this term, right? That's the idea. So make embeddings closer to the encoder output. Now they have also added a third term, something called as, they call this commitment loss. So what they're saying here is that the encoder output should not grow arbitrarily large. So that is basically they're adding some sort of a regularization on the output of the encoder also, right? And saying that, okay, whenever so whatever your encoder outputs, it should be close to the embedding vectors that we have. That's the idea. Okay, so again, when you're updating the encoder using this loss part, keep the embedding constant. Okay, so it's like saying you make encoder layer and the embedding layer close to each other, but while doing, keep one constant and then update the other, because it's possible they both can agree and will just end up, the whole thing will end up becoming null, right? So that's the idea. So this is called something called as commitment loss, and that's all they provide the intuition behind this. So therefore, at the end, the encoder gets updated from two terms. One is this decoder output, because this ZQ of x, you get gradients for ZQ of x. Those gradients will pass to ZE of x, and they will update the encoder parameters. That is one thing that will update the encoder, and it will also update the encoder, trying to make it more closer to the current embeddings that we have in training. That's the idea. Okay. So this is the final loss function for VQVAE. Now, all of this is good. So we'll get back to the main questions at hand. One is, how do you perform inference, right? So any thoughts? It should be very straightforward. How do you do inference here?
So inference is comparatively easier here.
Easier here.
You already have embedding vectors.
Right.
And the output z is closer to whichever embedding vector. That is probably
right.
That will give me.
Will be the inference, yes. Right? So basically, we just want to find out this Q of Z given X. Again, this is deterministic. So ideally what we just want is what is the K which gives me the argmin. That's it. That's it. That's the inference that we can do here, right? So the question now is how do we generate samples? Right, everything's deterministic here, right? There's literally there's no part of this whole flow which has any sort of randomness in it anymore, right? Previously we had, now we don't. So how do we do sampling here? So the way the authors propose to do the sampling here, and that's how they have done it.
That's normal, like centered on the embedding vector and having it.
But what is normal? What will be normal which will be centered around embedding?
Okay, that is correct.
Because they're all quantized.
Right.
So I can choose one of the this one. That's maximum I can do. Not more than that, right? And if I choose, there are only K, right? So you'll get only K outputs, but that's not what you want to do. So what the authors propose to do here is rather something like this. So what they say is, once you train everything, you collect all the ZE for all the points that you have in a data set, right? For all the points, you can get ZE of X, right? Then you fit something called as an autoregressive model. So autoregressive model, again, we will touch this a bit going forward, but the idea is this, that is you are able to generate values which look like your data using data that is already seen. So something like this, I'll give an intuition. So let's say I have an image, let's say, right? So I have a collection of these images, right? So instead of trying to model this in a separate way, rather what we will do is we will model this X, which is a multidimensional distribution, as a distribution over the dimensions of this input of this X itself. That is, let's say if I have k dimensional d dimensional here, right? So xd given xd minus 1 up till x1, then p of xd minus 1 given xd minus 2 until x1, and so on up till p of x1. And this is your usual. Sorry.
What are we doing here?
So basically we are trying to predict, let's say, the next dimension based on all the previous dimensions that I have seen, right? Yeah. So what will end up happening is, so all of these probabilities that you see here, they are themselves in some sort of a network, right? Which takes, for example, this all input and predicts a value, right? And therefore next one, right? And so on. So the idea is, if you fit a model like this on all these ZE of xi, you'll be able to generate new ZEs, new elements of your this embedding space. Understood. Right? Those you pass as input to your decoder. That is the idea.
It's not like.
Yeah, that's the idea, right? And people have said that, I mean, they have seen a lot that this training this VQA is very simple. This is the most difficult part. And that is sort of valid. I mean, one intuition why it's difficult is because it's autoregressive models and all. Basically, what they try to exploit the structure in that space, right? Now, so what we are hoping for is that the latents themselves have some structure, right? Now they may or may not have. They're going to be very independent and all of that. So it becomes a problem to fit any model on this, and therefore this is a challenge. So people have tried many different approaches here.
And autoregressive model itself is a model. So you are like first creating one model and then like using it for.
Yes.
Using an autoregressive model, itself you are able to generate images now. So why do you want to use the generated images to like train a VAE and then generate more images?
Okay, that is a valid idea. So yeah, so people have tried autoregressive model directly on images. So that is there. That's a whole work in other sense. Here, I guess the idea was, can we use, I guess, VAEs on discrete space, and if you try to do that, you will lose up on this sampling. You cannot get new things. So for that, you have to do something at the end of the day to get new images. I guess that's the thought process here. And more importantly, this one, so this VQVA model, which which the authors, brought it out, gave one of the state-of-the-art images for being generated from this, and that became a very strong moving point.
When did this paper came out?
This came out. I don't remember the dates though.
2021, 2019.
Maybe around that time, maybe. Yeah, yeah. I'll have to see.
Yes.
But this became a base for something called as Dowley model, version 1, and version 2 was diffusion model based idea. Yeah, so hence it became very famous, and this sort of idea took over. Hence this sort of thought process. Okay, so yeah, any doubts on these 4 methods: beta VAE, info VAE, VAM prior, VQ VAE? And there are many other versions that exist. So this idea called 2-stage VAE. So again, same thought process like this. So you'll have one VAE which learns your usual one. There's also another VAE which learns all the distributions of your of your latents, right? So that is a 2-stage VAE, and they show some results on that. Basically, that it is better to do it in that way than usual and all of that. So many different versions have come out.
Yeah. What are the applications of VAEs apart from generating images?
So VAs at least have that inference part coming in.
Oh.
That is a very good part from VA if you think about it.
Is it because we already have like so many convolutional neural networks to do this classification, or so many methods do this classification. So is VAE better than that in that classification, or?
Because what will end up happening, see, instead of dealing with a very large dimensional data set for your classification problem, you now end up looking at a simpler sort of a space. That is one point. So your curse of dimensionality, in some sense,
which also happens in like some other neural networks, because like ultimately they converge to some like lower dimensions.
Lower dimensions, it has to converge, right? So and more, and it's also possible that when you use a large dimensional input for your ML problem, let's say for classification or whatever, it's possible that the model can find some sort of very weird sort of method to solve the problem. At the end, the model is trying to look at, okay, can I classify or can I regress, whatever. This will sort of make sure that, okay, whatever information you have is captured in a low dimensional. You'll force it to, in some sense, to use very real sort of, relations between the output and the data. That is one intuition you can take. That's the third process, right? Okay. So this is one, whole idea on VAs and stuff, and we'll look at one idea called conditional VA. Okay. So conditional VA as so the use case will motivate the use case here. So let's say we discuss the idea of dogs and cats as an example, right? So let's say I have dogs and cats in my data set, and I also know what the image is, whether it's a dog or a cat. So now we have labels, right? So plus the labels of them. So then let's say I want to generate dog images only from this, right? So basically, so then the idea is that let's say I have, let's say, some X and I have a Y. This is the data and some sort of a label of that data. So what we want to generate is we want to generate something in this sort, X given by, right? So this is called as the conditional generation idea paradigm. So same thought process, but conditioned on something, right? That's the thought process. So so then the point is, how would the framework look like if we were to do conditional generation using the same sort of a thought, mathematical background. So So again, we'll go through it quickly. Let's say y is some class or some condition that you have in mind. So what we want to model is your p theta of x given y. This is your model for x given y. Again, that can be seen as an integral over x comma z. Z is some latent variable, and then we use this q of z given x comma y everywhere, right? So this is my expectation of this. Again, apply log Jensen inequality, etc., etc. Same thing you'll get to be like this, right? And then your so your even your elbow now turns out to be first term reconstruction with y, right? Generate x with z, and you'll generate z with x and y, and DKL term is also something like this, right? And again, same thought process. If you use neural networks, phi, theta, all the works, same thing, same ideas come out here. Again, thought process here is p of z given y again is taken as n0y. Yeah. That means doesn't depend on y also, by the way, right? Just take some sample, you will pass it through this. So here the idea is you will have an x, you'll have the label, you'll generate z. That z and that same label again will go as input to theta, your decoder, to generate the x. Right? That's exactly what this is capturing. Right? You need the latent, you need the label to generate x, and you will this q5 of z given x comma y. So you'll take x and y as inputs, generate a latent here, right? So basically here the bigger idea here is that your distribution that you choose, you will choose not only depending on x but also on the label that you have.
So basically, like, take all samples in which y is a particular label.
Correct.
And do the entire procedure.
The entire procedure. Yes, that's how it is. That's it. Right? Say simple, straightforward idea. Yeah. That's it. So this conditional VAE formulation.
There must be some variations to it, like rather than taking only y belonging to a particular label, take some mixture or like some.
No. Okay. So here's all labels, all data.
Okay.
See, that's why y is an input to this input to this model.
Okay. So y is not. So you're not only taking samples in which y has a particular value.
No. All samples. Yes. So all pairs of x and y from I equal to 1 to n.
As well as this data label information.
Yes.
Hoping that this label information will be used to like generate an appropriate.
Appropriate set. Yes, correct. Yeah, that's the idea. So basically, let's say if I have an x which looks more like a dog image, so then when I give y as, let's say, dog, your z should be able to tell me that okay, that this has a higher reconstruction sort of a thing. And if I give y is equal to cat, for the same dog image, the z should be will be shaped very differently or whatever, to telling you that okay, this is not the right thing to generate, right? Something like that. Okay. Fine. Now, this conditional generation idea is what underlies this thing that we have been looking, like, for example, image from text.
Okay.
Right? So we need to think about this a bit carefully. So,
image from text.
Right. So let's say if you look at this dolly, very recent sort of idea model here. So ideally, so if you give something like let's say dog in space as a text, right? So what you want is you want your model to be able to generate an image where I see some sun and Venus and all of that, and I have a dog here, right? That is the thing, right? So how do we go about doing something like this, right? That's the biggest question. So this is where conditional generation comes into play. So the idea is you will summarize this text in some sort of a vector. So ideally text processing systems like, let's say, LSTM or whatever, some RNN system, right? So what they will do is they will process this text as a sequence and generate a vector which is some sort of a summary vector of this text. Now, this summary vector is then fed into your decoder as your condition.
As a
condition. So this Y becomes a condition to the decoder, and because here how will you sample, right? Your sampling is you only have Y with you. Z you will still sample from N0Y only, right? So the way you'll sample here is Z you'll sample from N0Y, right? Regardless of whatever Y, whatever information you want to generate on X is dependent on Y. So Y has to give the nice information that you want your X to hold. So that is what is passed here, right? So you take Z N0Y, you put this becomes a condition to this decoder theta that generates this image. Different Z would give you this dog either play somewhere else or whatever, the interpretation of space changes, whatever, etc., so on. This is where the idea of this conditional generation sort of use case comes into play. Now this image from text. Now if you think about it, text from text, right? Something like ChatGPT sort of a problem, right? So where let's say so again from text, so what I will do is I'll have an LSTM, let's say, which processes sequence, gives me some sort of a condition, right? Some sort of a summary vector, right? This gets passed into the decoder, right? Again sample ZN0I, right? So for the same text, I can get multiple different responses, right? That is what comes out from here. Right. So if you were to, let's say, give the, I mean, ChatGPT has a lot more stuff in it. A basic version could be something like saying, okay, hi there, could be an input to the model. I mean, we give the ChatGPT as an input. Because I have some randomness, it could either give hello or hi, how are you doing, etc. So these are all the valid responses that you would want for this particular summary vector, for this particular condition. That randomness is captured by this is induced by this Z, and this theta is supposed to generate a text. That's the idea, right? So these sort of things they come from.
Train this model.
Sorry.
Like using the same framework.
Same framework you'll use. Yeah. So till now we have been saying, okay, image, right? Text if you want, you use, let's say, LSTM.
It's also like basically doing while training at least. It's doing text reconstruction only.
Correct. Oh. Yes, because it needs to be able to get what is the right text for this particular prompt, for this particular, let's say, input that you give. That's it. A very broad down version is that. Yeah. Okay. So lot other stuff is there.
So it's not like it's being trained on like question answer session, question only. You have a question, some black box and answer, and it's learning the mapping from there. It's not that.
Question answer. No. Yeah, it can't be that. It can't be that way. Yeah, correct.
So it's text reconstruction only.
Text reconstruction. Yes.
Okay.
Yes.
Understood.
And so
decoder is what matters.
Decoder is what matters. Yes, correct. That's the point. So yeah, so if you want text, you'll put this some text generation system, image. And so why? I mean, some sort of history here is previously we had this issue of image captioning. Now, what is this problem? This problem is not similar to this, if you think about it. I mean, sort of similar, but the point is this. Let's say you have an image. Text from image, right? So you have an image and you want to generate a text from this, right? So you could solve this in two ways. There is a non-generative way of solving this. This generative way also of solving this also, right? So the non-generative way.
You have samples, you have like output caption,
just train, right? Simple. So you have a CNN, hopefully, which processes the image, gets you some sort of a vector representation of that image. That goes into LSTM. It'll output text, learn it here. That's it. This input, this output, learn this mapping. One way of doing it in a bit more generative sort of way would be same VAE sort of approach only you can use. right? You can have a encoder which takes an image, seen in sort of a approach here, right? And then it passes out some summary vector that is passed to an STM and it gives a text out, right? So because images are already here and we know, so describing an image is easier than generating an image for a given text, if you think about it, right? So image captioning in some sense is a comparatively a simple problem to solve, whereas generating an image from a text is like an artist sort of many possibilities exist. The way you want to interpret the text completely changes and so on. That's the sort of a history why it comes from. So inverting this problem that takes a lot of challenge, and that's where these sort of things helped in some sense. Right? Okay. So this is the complete theory on VAs. So we're done with the theory that I wanted to do. PyTorch. So we'll do a tutorial in next class. So when we'll do it on Collab itself, so that we don't have any installation issues, etc. Torches are yes. You can join from there and stuff like that. So Torch is only present on Collab. You didn't install any as a extra library or such. So we'll do it on that itself, right?
So are you saying like after doing all these things, I'm good to go and like train VAEs on whatever I want?
Yes.
Or will it require something more?
No, because we have discussed exactly how to sample, how to pass gradients, everything. Right? Because that's the whole point. So in VAE formulation, when we came to this extension to multiple points, it's exactly where we discussed this idea. What should you apply gradient descent on? Right? We said minus LB. Fine. What is LB? We said, okay, LB is actually an expectation, all of that. We don't know all of that. How to operationalize it? I sample a batch of images, whatever of the data. For each element, I will sample ZB, pass through your encoder, get ZB, get sigma phi and mu phi, sample epsilons from this one, multiply, you'll get ZBs, pass them through your decoder, you will get an image. Simple, right? And DKL, the bigger point is that this DKL becomes a computable idea for every X. Just put that into your function. The PyTorch library will do the work of putting all the gradients down to your file, your encoder, right? That's it. So this is the idea. And we also spoke about this idea that, okay, if you take P theta to be a Gaussian, it becomes MSE. So at the end, you will just implement MSE only. That's what you will end up doing. That's it. And what we'll do is we'll do the basic version only, because again, info VA and all will require something more. VAM prior will require something more. VQ VA requires everything more. Only beta VA is something which you can do trivially. We just need to add beta. So, and you can see how it changes and stuff. That's something that.
So next class is what?
Tutorial, yes. So we'll do hands-on tutorial on Google Colab, and I'll see how much of the material should I already provide it, and you can just duplicate that notebook, or we'll see if we want to do everything from scratch. Right? That's one thing. So how much time we have? 5. So okay. So next class or next class, we'll discuss the idea of something called as adversarial learning. So I'll leave you with this mind thought process. Okay. So let's say, I mean, VAs, we saw how they attack the problem of generating a image, right? Using this variational approximation, all of those nice sort of thing. So what adversarial learning, in some sense, what we want to do is we want to attack the problem in terms of a random variable transformation approach. Okay. So we know that we have a function which will transform any random variable to another random variable, right? So let's say if I have a z, which is some known random variable, let's say uniform, Gaussian, whatever, what have you? Nothing. Just usual normal random variable I have, and then I have some function, let's say g, which transforms it to x, right? And again, why and we don't know G, so I will use a neural network to approximate this G, the true G that exists in the nature, right? Now, if it's a neural network, the idea is how do we go ahead and update, right? So the idea is this: G, I can initialize it, right? Because it's a neural network. So at the end of the day, let's say G, I'll say let's say G0. Okay, the initial parameters, right? Initial parameters, and then what I will do is I will pass all my possible Z through G of 0, and I will get, let's say, X0 sort of thing, right? Now we know for a fact that X0 is not X, right? For a fact we know. So how do we communicate the information back to G that, hey, look, X0 is not X?
Equation of error.
What error? That's the question.
Of X0 minus actual X.
But these two are probability distributions, no?
So these are random variables and probability distributions? Okay.
Right. So
then K divergence or like.
But okay, KL is between what? Okay, KL, okay, KL between what?
So what is random variable?
Okay.
X is random variable.
X is random variable, no?
Okay, and a probability distribution.
It has a probability distribution of Px, the true distribution, which we don't know. Right? X0 also has a distribution. Why? Because Z is a distribution, deterministic function. It's some distribution. Right? Let's say I'll call it Px0.
Yeah.
Right? So you said, okay, KL, fine. I'll do KL between these two. Right?
No, but like we don't know the prior distribution.
Yes. Yeah. So we don't know.
So I'll do mean square error.
Between what mean square you will do? What is mean square here?
We're starting with Z. We're getting X1. Okay, G Z itself we don't know.
Correct.
So we can't do MSE.
We can't do MSE.
So what would we do?
The MSE worked in VAEs. That's the point, because for a given X you'll get a Z distribution.
So therefore we can do.
Therefore we can do MSE.
But Z we don't know.
Here we don't know.
Okay.
Here Z is anything and everything. Any right? So yeah, think about it until the next class.
Or maybe we like use VAEs only.
No, we don't want to use VAEs.
Oh.
So yeah, in adversarial learning, no VAE without this variational approach. So I mean variational approach as such. So where you sort of build an approximate distribution which will approximate some other distribution. All of that sort of heavy math that we did. We don't want to do any of that. Very simply, can I tell my network, that is G, that whatever it has generated is not okay. Right? Some way we need to tell it.
The serial networks I understand. So.
That is fine. But yes, that's the idea. That's the thought process.
Yeah.
So how to update that we will go through, and then we'll see other issues. And so one thing, so we'll do adversarial learning in a very upper level. And then we'll move into diffusion models. Diffusion models will do properly, full math and stuff. And they're also distant cousins of VAs, so that'll bring out nice story in that sense. Right? Okay, so yeah, so we'll stop. Any doubts? No, so we'll stop here. Okay.